Okay, so again, we're talking about moving points around on a graph and what that looks like on a function. The easiest one to understand is probably y equals f of x plus k. This moves every point k units vertically. Make that k readable. So y equals x squared is a good graph to use for an example, but the same thing will apply to any of the basic graphs. And I assume everybody can instantly make a table for any of the basic function graphs and construct the graph and the extended graph. Okay, that's something you absolutely need to be able to do. Okay, so I'm just going to do the basic graph. And you should be able to draw it every bit as quickly as I can. You probably have more artistic talent than I do. So it's entirely conceivable you'll do it faster. There are my points. Now, I'm claiming that f of x plus k moves all the points vertically. So we want to do the graph of do f of x minus 3. I don't think I've asked you to do any graphs that move the points downward, although when you reflect graphs, sometimes that's what's going to happen. And if you understand everything we've done previously, I take this point, I move it down 3 units. I take this point, I move it down 3 units. And let's go ahead and get a scale on the y-axis. Oops, going too far.
Professor,
Okay.
on our assignments, do you want us to draw those arrows too?
I think it's a really good idea
Okay.
to do that, but I don't require it.
Okay.
But if you're having trouble understanding this, then it's really a good idea to draw those arrows.
Yeah,
And
I
I
was gonna
could
say.
ask you to draw those arrows on a test or somehow indicate how you've done this, because that allows me, in giving you feedback on your work, or I could ask you to draw the arrows on an assignment. It allows me to give you feedback on whether you're doing it right. If your points don't look right, I'm going to want to know why they don't look right so I can tell you how to correct it. Okay.
Thank you.
Yeah, go ahead.
I was just saying thank you.
You're more than welcome. Okay. So now I can sketch this graph. And of course, it's just this graph moved down. Well, if I make a table, for, you don't need an arrow on that, that's just, okay. So, right there is my table for y equals f of x. Now, if I want a table for this graph, I can see that this point is -2, 1. This point is -1, -3. This point is 1/2. -3 3/4, but I'll write that -15/4. 0, -3. It's not -15/4, it's -11/4. Okay. Yeah, 2 3/4. And these points could also be labeled. I don't have to label them all because you'll understand that. And if I make a table now for my f of x minus 3 function, and I want to emphasize I'm making this table
Wouldn't
based on the graph, not based on plugging numbers into this function. Go ahead, Lane.
I was saying that one point, the second point after -2, -1, shouldn't it be -1, -2? Right above it, right above the fraction. No, right above it. Yes. Shouldn't it?
Oh, you're right. It'd be -1, -2. I moved it down 3, but it was at 1. So thank you. Because that was not going to work. When I do the arithmetic, it's not going to work. So we got x and y here. So, okay, so now we've got -2, -1, -1/2, 0, 1/2, 1, 3. Now these numbers, I'm emphasizing that these numbers are not numbers that I calculate. These are numbers that I have to work out by what's going on with the graph. If I take this point, which is 0, 4, and move it down 3 units, it's going to go to 0, 1. The point, as Elena corrected me, where we have -2, 1, that's this point, that moves down 3 units and it goes to, and it's not -2, 1, it's -1, 1. -1, 1 will go down 3 units and that'll end up at -1, -2. And if you're not clear on that aspect of the graph, there's a very important thing that you're just not going to understand. So in the instructions for some of these assignments, I've seen people calculating these points instead of moving them. Okay. Now you could also get to it by calculating them and then seeing how far they moved. That would be equally good, but it's more direct to see how far these points move and figure out the coordinates. Among other things, you have to reinforce what it means for what the coordinates mean. Okay. Now we do this, we reason out where these points go. And, this one might be, fraction might be a little bit difficult, but you at least get this one, and this one. They're obvious because everything's an integer. So you're going to move to 1, and you're going to move to -2, and you're going to move this to -3, and this will move to -2, and this will move to 1. Okay. And then this one moves to, okay, it's -11/4. And this one moves to -11/4. I wrote that pretty small. It's not critically important that you get the right fraction here. Okay, you can get the principle just by the 5 points that have integer coordinates. So that's it. Now this is by the graphical movement of the points. Gives you all this. Well, everything's not just graphical movement. We can also do y equals f of x minus 3, which is x squared minus 3. By arithmetic. And I'm not even going to worry about the negative 1/2 and plus 1/2 points because I don't want to get involved in the arithmetic of the fractions, but that's something you need to know how to do. And if I ask you to do it, you need to be able to. Okay. Well, you get 1 because negative 2 squared minus 3 is 4 minus 3, which is 1. So not even looking at what you got from the graphical, calculate it. Okay, at negative 1, you get negative 2. I say negative 1, I write negative 1. I just negative 1 squared minus 3 equals negative 2. 0 gives me negative 3. That is 0 squared minus 3 equals negative 3. 1 gives me, I did it again. I said 1, I wrote 1. But fortunately, 1 does give me 1. So I looked out. 1 squared minus 3. No, it doesn't. It equals negative 2. And 2 gives me 1. And 2 gives me 1. 2 squared minus 3 equals 1. So there is the arithmetic. So it's very straightforward arithmetic. And if I look at the numbers I have here, they match the numbers I have down here. And if I figure this number out correctly from the graphical, it'll also match what the arithmetic tells me. So here's my arithmetic. And arithmetic and graphical agree. So do I have room? The arithmetic and the graphical reasoning agree. Again, if you've done the written assignments, even if you made some mistakes, you're going to understand this much better than if you hadn't. But it's something you need to understand. Now, I can do the same thing for y of x, y equals f of quantity x minus h. And I'm saying that moves 8 units in the x direction, h units in the x direction. Okay, so if we take the same function, the x squared function, a little high there. And we graph the same function. And we move these points 1 unit to the left. Now let's move it 1 unit to the right. No, let's move it 1 unit to the left. That's what I want to illustrate. Okay. So well, that means if we move this point over 1 unit, 1 unit is about this long. So like the origin will go over to here, and then every additional point will move over by the same distance. And I'll get a point here, a point here, a point here, 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 and here. And these points will be, well, this point is -2, 4. Again, I'm not going to write that down. You should know very well what that point is. If you don't, take a lesson. But this will be -3, 4. Because you're moving in the x direction, the x coordinate doesn't change. I mean, the y coordinate doesn't change if you move in the x direction. In this point, if you move it in carefully and understand what's going on and where these points move, this is going to give you the point -2, 1. You're going to get the point -1, 1. You're going to get this point, and if not -1, 1, it's -1, 0, and it's this point. So I'll clumsily make that 1 into a 0, okay? And you're going to get you're going to get 0, 1, and I guess I have room to put that in. It'll be up here, and 1, 4. You have to agree that these 5 points and the points that you get, -3/2, 1/4, and 1/2, and -1/2, 1/4. But I'm not going to label those. We won't bother with the arithmetic. Okay. These points will be on a table for f of x minus h. So h equals -1 because we're moving left 1 unit, which is -1 units in the x direction. Well, now,
If it was,
we can again make a table.
wouldn't it be? Isn't it right that when we move right, it's a minus, but when we move left, it's a +1?
No, that's the common confusion. That's why this one's confusing. Let me finish demonstrating it, and we'll see if we can make sense of it, okay? H is -1 because h is how far you move it in the x direction, okay? And we're moving this way, that's the -x direction. Okay, if we make our table for Shifting 1 unit left, I'll make an abbreviated table. I'm not going to bother with 1/2 and -1/2, although we could. Okay, we have 4, 1, 0, 1, 4. No, we don't. If I coordinate with my brain with what I'm doing, I wouldn't do these things. So believe me, I totally understand when you make similar mistakes, but you got to do like I do and test your mistakes against the reality. And then you find that you've made a mistake and you correct it. And really, I'm just pretending to make mistakes so that I can show you the process of correcting them. And of course, you don't believe that. You shouldn't. Okay. And I've still got a mistake. I corrected the wrong column. See how automatic it can become to write. Okay, the x values of these points are -3, -2, -1, 0, and 1. We can see that, yep. Okay. These points in orange have these coordinates. Okay, so -3, the coordinate is 4. At -2, the coordinate is 1. At -1, the coordinate is 0. And again, if you draw the graph carefully, you can easily reason out these coordinates. And then we have 0, 1, and 1, 4. Now, these coordinates match the points that we know we get by transforming the points on the x-squared graph. And now to keep things a little clearer, I can sketch the curves, the two graphs. And we see that this curve is just 1 unit to the left of this curve. Now, by the arithmetic, y has to equal f of x minus h. H is -1. So this is f of x minus -1, which is x plus 1, which is x plus 1 quantity squared. So now, for my x values, if I plug in x equals -2, I get -2 plus 1 squared that's 1. I plug in x equals negative, so I get 1. If I plug in negative 1, I get 0. If I plug in 0, I get 1. If I plug in 1, I get 4. And if I plug in 2, it turns out I get 9. Okay, well, negative 2, 1 is a point on this graph, isn't it? So using x plus 1 squared, which is x minus negative 1 squared, gives me the number that agrees here. And I get these numbers as well. I don't get this number. If I do it by arithmetic, you can verify if x is negative 3, x plus 1 is negative 2, and negative 2 squared is 4. And then I get the 1 and the 0 and the 1 and the 4, just as I did before. So the coordinates I get from doing this on the graph without calculating anything match the coordinates I get if I do f of x minus negative 1. If I did f of x minus 1, it doesn't work. F of x minus 1 is x minus 1 quantity squared. And you can do your own arithmetic. If x is negative 2 at negative 3, so let's compare with this table. X minus 1 is negative 4, and I get 16. And I'll make a little, I don't really have a good place to make a note, but I'll do this. Just for this one calculation. Now that might be a little hard to read, so let me move the board over. My point is, if you use this function, it's not going to match. It's not going to move the graph 1 unit to the left. Negative 2 is going to give you 9. Negative 1 is finally going to give you a number you can use. And then 0 and 1 will give you 1 and 0. And it turns out that this graph moves everything 1 unit in the positive direction. So you should try to understand this by doing a graphical shift of a basic function and comparing what happens if you do f of x minus 1 to what to get if you do f of x plus 1. Okay? It should convince you that this motion is exactly in the opposite direction of what it looks like it ought to be. And there's a good reason for that. to get the same number out of f of x plus 1, x has to be 1 less. In other words, to get the number out of x plus 1 that you get out of, to get the number you get by squaring x plus 1, the number you square has to be 1 less than the number you square to just get x squared, okay? And I still didn't say that very well, but that's the way it goes. Okay, so that's this transformation. And at a very minimum, you need to be able to do these transformations for whatever number h or whatever number k for the basic functions. And this is why we spent 2 weeks on written assignments, just moving points around and doing estimates. So you get a deeper, visceral understanding of what's going on with transformations, because most of the course is involved with the basic functions and the way they're manipulated. And there are only 3 ways they can be manipulated. One is by adding, subtracting, multiplying, or dividing 2 functions, which is fairly easy to understand and fairly easy to do algebraically. Although if you try to analyze them algebraically, you can get a little hairy. But okay, you can do that. You can do composites, which we've talked extensively about. And you can transform them. And transforming them gets you out of just the shape of the basic function, allows you to make it wider or narrower, skinnier or fatter, and put it anywhere on the coordinate system that you want, which then gives you the whole range of functions that we usually use in modeling the real world. The most common functions you use in modeling reality are these basic functions and their transformations. Then you get around to doing composites, which are very important, or sums, which are important, or quotients or products. Okay, well, that's why this whole process is fundamental, why I've been asking you to do a lot of work on it. Now let's go on to the other transformations, like the one that we get. Yeah, I'm going to need this one, so that's all right. Okay, y equals a times f of x multiplies y values of f of x by a. In this, moves points a times further from the x-axis. Vertically, that means up or down, because the y-coordinate, if you change the y-coordinate of a point, only the y-coordinate, you're moving it up or down. So it moves a times further vertically. And on the other side of the x-axis, if A is less than 0. Now, when I say it moves at A times vertically, I've got to put an absolute value around that. Okay, if A is -3, then it moves the points 3 times further, but it also then moves them on the other side of the x-axis. And you've seen that transformation in the homework, the written assignments. Let's use our good old x squared function. I'm going to use y equals 3x squared. Now, one thing about 3x squared is it's a little inconvenient because if x is -2, we're going to get 12 here, so we've got to have a pretty extensive y-axis, but we can handle that. So I can see in advance that if x is -2 or 2, this is going to give me y equals 12. Now 12 is a little bit less convenient to subdivide. And pretty hard to subdivide accurately, as you can see from my errors here, but there's 12, down here is 6. Down here is going to be then 3 and 1, and then you got your 1/2 and 1/4. 4 is going to be here. I don't have a good place to label it either, but that's where -2 is going to go. So -2 is going to go with 4. -1 is going to go with 1, which would be about here. -1/2 is going to be really close to the axis. So I'm going to kind of gloss that one over. I almost went up here, that would have been that. So here's my x squared graph. Now it looks a little flatter than I usually draw it, but there's nothing that dictates exactly how you're going to scale your y-axis. If you got 100 here, then this graph is going to look pretty flat. If you got 1,000 here, this graph is going to look like just almost a line along the x-axis. So that's an important idea, but we're not going to do anything with it today. Okay, so here's my y equals x squared graph. Then y equals 3x squared means you're going to move every point 3 times as far. So it means you're going to go this far, and then you're going to go this far, and you're going to go this far, and you're going to end up here. Now, since this point is -2, 4, that means you got to go 4 units here. Then you got to go another 4 and another 4. And you can do that. You can count on your fingers almost. 4 and 4 and 4 is 12. So this point is -2, 12. Okay, well, now this point is just going to move up 1, 2, 3 times as far from the x-axis. Again, each of these arrows represents how far the x squared function, the point on the x squared graph, is from the x-axis. Also represents whether it's above or below, but all the points are above this time. So, okay, so that gives us a point here. And this point is -1, 3. And you don't figure that out by plugging -1 in for x, although that's really easy to do. You figure that out from the fact that this is 1 unit, and then we go 1 more, and we get up to 3 units. And of course, 0 is right on the x-axis, and 3 times as far is still on the x-axis because you're not off of the x-axis. So we're going to get 0, 0, and there are no arrows to draw because the distance from this to the x-axis is 0. It's just a point. Okay, so then we do this here and get a point. And then we slap 3 arrows together. Yeah, that's about right. You get this point, and now we can sketch our graph. Oh boy, I really missed out. How did the graph? It is 4 times as far. I'm gonna have to correct that. My hand was blocking this point. Which is not an excuse. I should have looked around my hand. Okay, so there's our parabola. It's stretched out by a factor of 3. Vertically stretched by a factor of 3. There we have it. Then we can do the tables. We haven't calculated these coordinates, but graphically, we see that the points have to be -2, 12, -1, 3, 0, 0, 1, 3, and 2, 12. And then using arithmetic, for example, we do get 12 here because we plug in -2 and we get 3 times the quantity -2 squared, which is 3 times 4, which is 12. And I'm not going to write out now, right? 3 times -1 squared equals 3 times 1 equals 3, etc. And these agree. Okay. Now I'm going to talk a little bit about inverse functions, very little because we've only got a few minutes left here. And I will run about 5 minutes over because we started 5 minutes late again. My error. So if you have to go, you may, but you can. Watch the video if you need to. All right. So inverse of the y equals 2 to the x function. First of all, we do a table for the 2 to the x function. And there's no surprise here. We get these numbers. Okay. Y equals f inverse of x. And I'm not going to say what the name of that function is just, yeah, okay, I will. That turns out to be the log base 2 function, but we're going to deal with log functions a little bit later. Still, this is my favorite illustration of an inverse function and the least complicated. Okay, to get a table for this function, all you do is you take the x column here and you write it down as the y column. And then you take the y column and write it down as the x column. In other words, you invert these two columns and that gives you the inverse function. Okay, well, you know that the graph of this function looks like this. Okay, well, let's do the graph of this function. Now, one thing is your x values, matter of fact, let me fix this. Your x values are all positive, so I don't need to have as much of the negative y-axis on the graph as I did. That'll allow me to draw things a little bigger, which will be helpful. So I'm going to put my y-axis about here. Notice that my y values go from -2 to 2. So I'll put -2 here and 2 here. Then I'll have 1 here. And I'll have -1 here. And then for y values, that's all I'm going to need. X values are going to go from 1/4 to 4. Well, here's 0. I'll put 4 out here as far as I can. And then I'm going to have 2 here, 1 here, 3 here. And then I'm going to have to have 1/2 and 1/4 because those are X values. Then I just plot the points. 1/4, -2. Here's 1/4. I'm down to -2 and I get a point. Here's 1/2, -1. So here's 1/2. Here's -1 on the y, so it's going to be there. And then 1, 0, that one's easy to graph. And then 2, 1, well, that's easy. And 4, 2. Going to be about here. So there are my points. That's the basic log base 2 function. And the extended basic function just by sketching a nice smooth curve. Now, how does this curve compare to this curve? If you do this exercise yourself, it will help you understand things that you see in the text. Right there are the two curves. Haven't drawn them really that great, but really not too badly. Here's the line where y equals x. Just a line that goes at 45 degrees if you use equal scales. I'll simply observe that if you take any point on this graph and then move perpendicular to this y equals x line, again, provided you have equal scales on your y and your x, you get a point on this graph. And that the points in this graph is has coordinates A, B, whatever A and B are, as long as it's a point in the graph. And what are the coordinates of this graph? On this graph, this point is BA, because the coordinates of points on this graph are in the opposite order of the coordinates of the points on this graph. Well, that's pretty fundamental. Now there's more to it. And it's not going to hurt if I get to talk about inverse functions for another class. So I want you to get started on the section 1.6, but I'm going to change the due date and have it due on Friday rather than Thursday. Okay? Give you an extra day to do that. Because there's more that I kind of need to tell you here, things that might confuse you. But do everything you can in the meantime. Try to get at least half the assignment done, because you don't want to have to think it all through on Friday. You want to think through as much as you can between now and then and go from there. Okay?